We're making progress. We're going to look at video 4.2, simplifying fractions. And this is a very important piece to all the computations that we'll be doing. To perform operations on fractions, it's necessary to be able to factor a number, and that's what we're going to start with today, is how to factor. Factoring a number means writing a number as a product. In other words, we're going to show it in multiplication. So we have two kinds of numbers. We have prime numbers and we have composite numbers. Prime numbers have exactly two factors, the number and 1. So we know numbers like 5, we can write that only as one way in multiplication. Composite numbers have more than two factors. And like 6 would be 1. 6 would be a composite number because we can write that as 6 times 1. We can also write it as 2 times 3. So it has the factors of 1, 6, 2, and 3. So we're going to look at some numbers and decide if they're prime or composite. 2 would be prime because we can only get that by multiplying 2 times 1. 78 would be composite because as an even number, it can be divided by 2. So we know we have 1 times 78, and we also have 2 times 39. And there may be other ways as well. 51 looks like a prime number, but it's not. It's a composite number because besides 1 times 51, we can also multiply 3 times 17. 19 is prime, 31 is prime, 3 is prime, 57 is similar to 51. It is composite because besides multiplying 1 times 57, we can multiply 3 times 19. 29 is prime, 34 is composite. It's an even number, so we know we could multiply 2 times 17, besides 34 times 1. 17 is prime. So what we're going to do is we're going to look at some techniques for finding what's called the prime factorization. In other words, we are going to write the number as the product of only prime factors. So to do that, we need to look at these divisibility rules. Only 2 of these I ever use. So I'm going to share those with you. You can look at the others. 2, we know you can divide a number by 2 if the last digit is even. We also know about 5. You can divide any number that ends in 0 or 5 by 5. 3 and 4, there's a rule for that. You're welcome to learn it and use it. I think it's kind of cumbersome and hard to remember, so I don't pay much attention to it. And 9 as well. So we're going to look at 2 ways to find the prime factors of a number. The first one is called a factor tree. The other one, I don't know what the name of this is. I've seen it in a number of books, but it's never given a name. It just shows you the method. So I've given it a name. I've called it the division framework. I don't know. Factor trees, we're going to start breaking these numbers apart into 2 factors until we get to the end of every branch of our tree, our upside down tree. That is a prime number. So we'll start with 72. I know we can break that down into 8 times 9. We could also break it down into 2 times 36. It doesn't really matter where you start. It just matters where you finish. So let's continue on this one, and then we'll compare it to the other one that I started. We know that 8 is 4 times 2. 2 is prime, so we're done with that branch. And now we're going to look at the 4. We can break it down into 2 times 2. So the ends of those branches are prime. So we're finished with that side that's the 8. 9 is a composite number, and we can break that apart into 3 times 3 and those are both prime numbers. So our prime factorization of 72 would be 2 times 2 times 2 times 3 times 3. And we can write that with exponents. We would have 2 to the third power, because we're using it as a factor 3 times 3 to the second power, because we're using it twice. So this is the prime factorization of 72. Now let's take a look at this first one that we started. 2 is a prime number, so we're done there. We can look at 36. We can break that down into, 2 times 18. 2's prime. 18 we can break down into 2 times 9. 2's prime. And we can break down 9 into 3 times 3. And 3 is prime. So what you have is 2 times 2 times 2 times 3 times 3, which is the same thing we got. That's the reason I'm kind of partial to this particular technique, because there's lots of ways you can do it. There's not one right way. If you do it correctly, you'll come up with the same prime factors at the ends of your branches. So let's do 56. There's several ways you can do this. I'm thinking 7 times 8. 7 is prime. 8 is not. 2 times 4. 2 is prime. 4 is not. We can break it apart into 2 times 2. So we have 2 times 2 times 2 times 2 times 7. And if you multiply those together, you get 56. So in exponential form, it'd be 2 to the third power times 7. Okay, here we go with 60. 60 we can break apart. 6 times 10. 6 is not a prime number, so we can break it apart into 2 times 3, and both of those are prime. 10 is not prime, but we can break it apart into 2 times 5, and those are both prime. So the prime factorization of 60 would be 2 times 2 times 3 times 5, or 2 squared times 3 times 5, written with exponents. And lastly, we have 45. I'm going to break that apart into 5 times 9. 5 is prime. 9 is not. We can break that apart into 3 times 3, and both of those are prime. So the prime factorization of 45 would be 3 times 3 times 5, or 3 squared times 5. That's written in exponential form. Now we're going to take a look at the other technique, which I'm calling division framework. We're going to divide the number by the smallest known prime number of the number, and then divide that quotient that we get after we divide this first time by the smallest prime factor, and we'll continue until the last quotient, or the last answer we get, is also a prime number. So to be helpful, I'm going to list the prime numbers: 2, 3, 5, 7, 11, 13, and so on. But I think on the numbers that we're using, we won't have to divide beyond that. So let's start dividing 72. We'll start with this one, 2. So we'll divide by 2, which is 36. We can divide that by 2, which is 18. We can divide that by 2, which is 9. 9 is not even, so we can't divide it by 2. So now we're going to move down to the next prime number, which is 3. We divide it by 3, and we get 3. So 3 is a prime number, this final quotient that we got. So these are the prime factors: 2 times 2 times 2 times 3 times 3. 2 to the third power times 3 to the second power. And you can see when we factored 72 using a factor tree, we got the very same thing. It's just a different method. I think this gives you more freedom in how you're thinking. Some students love this, whatever you want to do. Okay, next we have 56. That's even, so we can divide by 2. which is 28, which is even. We can divide by 2, which is 14, which is even. We can divide it by 2, and we get 7. And 7 is on our list. So here are the prime factors of 56, just like we had up here. 2 times 2 times 2 times 7, or 2 to the third power times 7. 60, we'll start by dividing it by 2. We get 30. We'll divide it by 2. We get 15. We'll divide it by 2, and we get 5. So we're done. 2 times 2 times 2 times 5. Oops. I take this back. When we get to 15, we can't divide by 2. We can divide by 3. Sorry about that, which is 5. So we have 2 times 2 times 3 times 5, which is what we got up here. The last one is 45. It's not even, so we can't divide by 2, but we could divide by 3, which is 15. We could divide it again by 3, which is 5. So here's our prime factors, just like we got before. 3 times 3 times 5, or 3 squared times 5. Next, we're going to start talking about comparing fractions. Whether they're equivalent or equal, both represent the same portion of the whole. That's what that means. It's just a different name for it. So we're going to talk about simplifying these fractions in a moment. But first, we're going to talk about checking with the cross products. The cross products, if they're not equal, then the fractions are not equivalent. So I'm going to look at this first two. Cross products means I'm going to multiply crossways, and I'm going to multiply crossways. This product, 6 times 8 is 48. And now I'm going to check this product. 24 times 2 is also 48. So these are equivalent or equal fractions. Let's look at the next two. Are these equivalent? Are they the same? Well, we can check. 10 times 40 would be 400. And 25 times 16 would be 400. And so these are also equivalent fractions. We can look at pictures. We've seen this picture before where we started with a third. Then we divided it into 2 places, each piece into 2 pieces, and we had 2 sixths. Then we divided those into 2 pieces, and we ended up with 4 twelfths. And these are all equivalent fractions. And again, we can look at them on a number line. These top ones show the distance between 0 and 1 divided into 3 parts, so this would be a third. These pink ones on my paper, we've divided into 6 pieces, and so this point right here is 2 sixths. And if we look at the actual number line, it's divided into 12 pieces, so we have 4 out of 12 that are to this point right here. So now we're going to go back and take a look at simplifying the fractions to see if they are equal to the same thing. So the simplest form, or as I learned it, the lowest terms of each fraction, and terms are just the numbers, the top and the bottom, is when the numerator and the denominator have no common factors other than 1. So you can't divide them by anything but 1. So let's look at these fractions. 9 twelfths. Well, we're going to divide the numerator and the denominator by the same number. And I know my multiplication facts, so I know I can divide 9 by 3 and 12 by 3. So really, I'm dividing by 3 over 3 or dividing by 1. And we know that really doesn't change things. So we would have 3 as a numerator, 4 as the denominator. That's in simplest form, or the numbers are the smallest they can be, which is lowest terms. 5/10, it's easy to see that we can divide both of those by 5, and we end up with 1/2. 3/18, we can divide numerator and denominator by 3, and we end up with 1/6. 6/8, we can divide 6 and 8 both by 2, and we end up with 3/4. So we've simplified that in one step. We know our multiplication facts, so those come to mind quickly, common factors of the numbers. Sometimes they don't come to mind as quickly because maybe the numbers are bigger or they're a strange combination. So you can use a multi-step process if you want. 15/90. I know right off I can divide both of those by 5. 15 divided by 5 would be 3. 90 divided by 5 would be 18. And now when I look at 3/18, I see there are common factors. You can divide them both by 3. 3 divided by 3 is 1. 18 divided by 3 is 6. I'm not sure why this next one is in there, because I can see I can divide both of those by 5, and I have 3/8, and I'm done. So I don't know why that's on the list, but it is. 48/56, we can divide both of those by, by 2, and we get 24/28. And we could divide those by 2 again, or I can look and say, oh, I know I can divide both of those by 4, which would be 6/7. So however you do those, you might have another step in here. You might divide both of these by 2, and you'd get 12/14, and then divide that again by 2, and you would get 6/7. So my point is, sometimes just moving ahead and dividing by an apparent common factor, and then in the end you have to divide again, may be the smartest thing, rather than sitting there struggling over, what's the greatest common factor that both of these numbers have? So we're reminded that multiplying negative fractions is the same as for positive fractions. So if they have the same signs, it's positive. If they have different signs in multiplication, then the answer is negative. So, if you break these apart with the with the prime numbers, with the prime factors, you can actually see that this fraction, 10/27, does not have a common factor. There's a 2 up here, but not below. There's a 5 up here, but not below. There's 3s down here, but not up here. So we say that this is in simplest form. So let's take a look at how do you simplify fractions that have variables or letters in them. Well, the very same way. Here we have 10xy over 6x. So I factored the 10, 2 times 5. X is a factor, y is a factor. The denominator, we have 6x, so 6 would be 2 times 3 times x. So now I'm looking for common factors. We have a 2 top and bottom. We have an x top and bottom. So we're left on the top with 5 times y, and on the bottom we're left with 3. Okay, let's look at the next one. 18d over 15 over cd. So I factored 18. 2 times 3 would be 6, times 3 would be 18, times d. and the denominator would be 15, or 3 times 5 times c times d. So I'm looking for common factors. There's not a 2, but there is a 3, so I can cancel out one of the 3's. There's not a c, but there is a d. So we have 2 times 3 on the top, which is 6, and 5c on the bottom. This next one, we have x's on the top and x's on the bottom. So I factored the x's. X squared would be x times x. We're using as a factor twice. And 60 x cubed would be 6 times 10. We're making this kind of simple. We could have done it 2 times 3 and 2 times 3, but and x cubed would be 3 factors of x. So I got a 6 above. I'm going to divide both of those by 6. I've got an x top and bottom. I've got another x top and bottom. So on the top, I've canceled everything out. Every time we divided by 6, we got a 1, we got a 1, we got a 1. So we have a 1 on the top, and on the bottom we have 10 times x. The last one we're going to have to do ourselves. So 9 would be 3 times 3. W squared would be w times w. And I'm not sure that you had these numbers on your copy originally. So double check and be sure you're working the same problem I am. 36w squared, 36 would be, I don't know, 2 times 2 times 3 times 3. That's 4 times 9. Times w times w times w, because we're talking about cubed. Okay, I see it. We can divide by 3 and divide by 3. We can divide by 3 and by 3. We can divide by w and w and w and w. So on the top, we're left with 1, and on the bottom, we're left with 2 times 2 times w. So that would be 4w.